In this video, we're going to talk about modeling exponential growth and decay. So we start with our function y equals a sub 0 e to the kt. And exponential growth is when a quantity grows without bound, often referencing the doubling time of the scenario. And doubling time is the time it takes for the quantity to double, as it kind of sounds like. Now, exponential decay is when a quantity is falling rapidly towards zero. Half-life is a concept we use in there in exponential decay often. That's the time it takes for a substance to exponentially decay to half its original quantity, and we've talked about that in other videos. Characteristics of the exponential function y equals a sub 0 e to the kt. So an exponential function in that form has the following characteristics. It's 1-to-1. Horizontal asymptote is y equals 0. Domain is negative infinity to infinity. The range is 0 to infinity. The x-intercept, there is not one because it doesn't hit the x-axis since it's a horizontal asymptote. Y-intercept is at 0, comma a sub 0. That'd be like an initial value. Increasing if k is greater than 0 and decreasing if k is less than 0. So we have two graphs here. This is an example, one here on the left, of an increasing function. So it's exponential growth. And over here on the right, it's a decreasing function, exponential decay. So our k is negative in this case. So example 1, a population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. And I put a really tall graph here. I think I can get it most of what we need with this scroll to this point. So anyway, let's go ahead and come up with our equation. And now our initial amount, let me start up here. Our initial amount is going to be 10 bacteria. And after 1 hour, it will have doubled. So when t equals 1, the amount at time 1 is going to be 20. So, excuse me, if we have a of t equals a sub 0 e to the kt, 20 is what happens after an hour, is equal to 10 e to the k times 1. So divided by 10, 2 equals e to the k. The natural log of 2 is the natural log of e to the k, but that cancels, so natural log of 2 equals k. And k is approximately, I think it's 0.69, isn't it? They left it as natural log of 2 in the power. Okay, so we'll do the same thing. So the amount at time t is going to be equal to 10 times e to the natural log of 2 times t. Now we can play with this a little bit more. This is the fun part about algebra. A of t is going to be 10 times, I think of it this way, this t is like a coefficient, so that can be made a power of 2. E to the natural log of 2 to the t, and an e to a natural log would cancel, and that leaves us with a of t equals 10 times 2 to the t power. That's kind of a nice formula to come up with. And so we know it, a at 0 is going to be 10, and a at 1 is going to be 20, as we talked about. A of 2 is going to be doubling that, so 2 to the 2 is 4, so 40. A of 3 doubles again, it's going to be 80. A of 4 is going to be 160. A of 5 is going to be 320. So we're getting beyond where my graph goes. So we start off at 10. Let's go to red for that. Change colors here. Start off at 10. After the first hour, we're at 20. After the second hour, we're at 40. After the third hour, we are at 80. In the fourth hour, we are at 160. And then the fifth hour, we are going to be beyond this graph. So growth looks something like that. Yeah, it's kind of fun.